This conference will now be recorded.
Okay.
Okay. Yeah, so I'm going to talk about system level tests, which I'll call SLT for the rest of the meeting. And this isn't necessarily a chiplet play, but I think it could be very useful in chiplets as well. And maybe that's a good point for the discussion. So I'll start by just saying what system level test is. So here, what we're trying to show here is what the what the normal chip test is. This is looking for for production faults rather than functional faults. So this is a production test flow. Normally, you can do a wafer level test using probes. And then when you cut and dice the individual chips, you can package them and then do a final test. The 93K there is a particular platform that we use a lot, but it's an automated test environment. And then you do your final test, and then basically system level test sits after the final test. So normally that final test there would have been the end of the story. So if this final test would normally be the end of the story. SLT sits in here, and I'll tell you why it's becoming more prevalent, this system level test. Okay, and what the drawbacks are as well. So it's not all good news. So if we look at the definitions here, system level test is the ability to test a chip or multiple chips in a package, and that's a key thing maybe for chiplets, is that multiple tests in the chips in the package in the context of how it will be ultimately be used. So the reason we call it system level test is a sort of use case system level testing, and use cases quite often how it's described as a use case test. And can ATE do system level tests? It's mainly ATE, the sort of automated tests which we're normally thinking of, which are this part of the pre-SLT flow, are normally focused on block first. You put your scan chains in, and you scan in your test vectors. You do your single cycle, and then you scan everything out again. So it's very block focused, whereas SLT is focused on the whole chip. And also it doesn't really, structural test, ATE doesn't really put the chip into environments in which it will be used, in terms of like thermal hotspots, for example, that might get produced. And we're seeing in the next couple of slides that doesn't always catch all the bugs anymore, or all the production issues anymore, the faults. So this is a typical SLT setup. You've got a reasonably complicated board there. That's that, because you need to put the chip into a system level context. So you're sort of trying to mimic how it will be used eventually. It's like a validation board. But if you want to get high volume, and normally if you're doing this for if you're doing it in the production flow, you need high volume SLT. This is going to become more and more complex. But most of the big test equipment manufacturers now are doing high volume SLT boards as well, with the handlers. Okay. So that's hopefully giving you some context of what SLT is. If you've got questions, feel free to ask. I'm happy to stop. What's driving it? So this is sort of marketing data that's available on the web. Nothing specific here, but the what's driving this from our perspective is these markets, is the memory and storage market that's got very, very high speed protocol interfaces, but maybe we can't find all the faults from structural test. Computing environments, AI, edge, with a lot of thermal management, a lot of heterogeneous systems integration going on. Automotive that have very high quality thresholds and DPPM targets, and in the mobile phones where you've got very, very high level volumes, so just a few escapes can cause you high numbers of returns. As I mentioned, that most of the major ATE equipment providers are now doing something SLT, so it's starting to become mainstream. Teledyne, Adventest, I don't, these are the main ones. They're all doing something in Adventest. There's some links there if you want to go off and look at it. The key trends are, so lower technology nodes drives the higher number of untested transistors. And this is, I guess that's the key thing, is that in structural tests, we're starting to see more and more untested transistors in our structural test flows. Concurrent scenarios that drive complex test scenarios that you can't.
Hey, Mike.
Yeah.
One quick question: how do you know that they're untested? Is it because they just weren't toggled at wafer sort or something?
Yeah, well, you get returns from the field. One interesting scenario that we're working with a customer on is they use SLT to find holes in their ATE. So basically, what they're using SLT for is effectively do bench validation of the chip, so that they push all their chips through their standard ATE flow, and then put them in SLT flow, and then they try to find manufacturing faults in that SLT, and then from that they can analyze what holes they've got in their structural test and then backfill the structural test. So they avoid high volume SLT by using the SLT as a coverage analysis, if you like. And then you miss any extra faults they find, they push back into the ATE. And what they're saying is through this, they are starting to find untested transistors that weren't tested from their normal ATE development. They can find them in the SLT. And some of them, and then you've got a choice. You can either start to do it high volume SLT to find those bugs or those faults, or you can then take that fault, work out how you can then detect that fault via structural test. But what they're saying is that there are untested transistors from that analysis. Does that make sense?
Yep, it does. Thanks.
Yeah.
And then quick question, what's the ATE stands for?
Automated test environment. So that's the normal high volume structural test that you would do. So you'd have thousands of hundreds, thousands of chips being tested in parallel, and the test vectors scanned in. You clock them and you scan out the results and you're typically looking at stuck-at faults. But they're the high volume automated test environments that Teledyne, Adventest, etc. Are used to providing on the foundry floors. So they typically, you got your fault model with stuck at 0, stuck at 1, maybe some bridging, and by providing those structural tests, you can find those manufacturing faults very quickly, and you use your ATE, your automated test environments, to do multiple chips in parallel. So if you're doing a mobile phone and you're trying to bang out millions of chips a month, you need to be able to test those chips for manufacturing faults in high volume, and the ATE allows you to do multiple chips in parallel. Does that make sense? Is that okay?
Thank you. Yeah, great. Thank you.
Yeah. So these are just very, very high volume, and it's all robots as well. I mean, the chips are placed inside let's just think of an ATE test environment. It's got 1,000 slots for 1,000 chips to be tested in parallel, and then robots that will load those chips for you. The test may run in 5, 6, 10 seconds, and then what you do is you bin any chip that fails at those tests will be binned, and any passing ones will be go off for that are okay to go to market effectively. But it's because you're in a mobile, for example, mobile environment, you're trying to get millions of chips a month potentially. You need highly parallels, highly environments with lots of robots doing the work for you.
So, Mike, that leads to the logical question: when you've got 10 chiplets in a package and no chiplet has been tested fully, how the heck is that going to get tested to a
well, that's a good question, because we had the known good die presentation before. I don't know if you attended that known good die, and I think basically we were saying that a good flow for chiplets is to make sure you've tested those die before they go into that chiplet package, you've assembled them, and what part of this presentation will talk about how you can then potentially use this to test them once they've been packaged as well, because even if you've got 10 known good die, when you put them onto the chiplet package, you can introduce faults again, so that you need to retest them in situ as well, and SLT might then be a good environment to do that in, because you could then put them into effectively the end user environment and get high coverage of the overall system from that. So that overall system approach might work very well just in a for the overall system on chiplet, I guess, you might want to call it. There's some other trends there that are pushing us towards this as well. The concurrent scenarios, a lower VDD creates high concerns for guard band stack and yield overkill. So basically, our guard band is getting squeezed. Dynamic voltage and frequency scaling is being used more and more, and that again can produce more manufacturing bugs or less guard band. And also trend number 5, for example, conventional test methods that the stuck at no longer catch the new possible faults for lower technology nodes. And number 6 as well is an automotive example where use cases are becoming for devices that are mission critical and that with 0 DPPM quality levels, because you probably can't reach 0 DPPM just by using structural test and ATE. So there's a lot of trends pushing us towards this, and I think chiplets is probably another trend that's going to push us towards this as well. So this is an old proof of concept we did for an SLT, and basically the thing you should take from this is that this was just a single chip in the middle there. That sort of yellow in the middle was the chip that was under SLT. The picture you're trying to put across here is that it's a complex environment. You've got lots of USBs in there. You've got lots of temperature control. You've got an external PC that's driving all this and analysing the results. And that was just for a single chip inside a socket on the load board with a PC connected. So that's a very, very complex environment for this single chip, and that's a proof of concept we did about 2 or 3 years ago, and we're updating that now. But these boards and the environments in which they sit are very complex, but they are cheaper than an ATE. So going back to that conversation about ATE millions of dollars. So an SLT environment is cheaper in comparison, even though this looks quite complicated. And then the types of system level tests, you're typically driving use case scenarios. Okay, so and you can see here, this is this project in a little bit more detail, and the types of tests you write, the SATA test, CAN tests. So you can probably see it was an automotive chip. Boot via the USB, audio display, CPU stress tests, eMMC reads and writes, DDR stress test, SPI, I2C, and the micro SD. So you're really using every interface and lots of different scenarios on that chip to put this through an SLT. And what this shows us is that it's a big embedded software development play as well. So it's not just about developing hardware boards and placing the chip inside that hardware board. There's a lot of software development going on as well, because effectively you're this is a chip evaluation scenario, and you need to run lots and lots of software to put that into that into a use case scenario. So there's a couple of projects that we've worked on where we've been doing the embedded software development, and there's a lot of types of software that's gone in there, and the different types of boots, and a number of systems per handler. So this line here tells you how many chips are being tested in parallel. A lot of the work we're doing at the moment is still very much where companies are still trying to bring themselves up on this type of technique. And in an ATE, you'd be doing thousands of chips in parallel. So these are low numbers, but those ATE equipment manufacturers are now starting to ramp up to, I think the most I've seen is about 1,000 chips in parallel in an SLT environment. So that allows you to start doing SLT in volume. Okay. And here's the environments. This is a compute chip we're working on, and that you can see the chip here is being put into that board there. And again, you've got the external laptop or computer that's driving this whole environment. And based on this, you can see that we only have 8 of these in parallel, but the equipment manufacturers are now allowing us to put do 500 of these chips in parallel in these environments now. But they're still complex environments. And this is the other one. This is a AI configuration that we're working on. Okay. So that's sort of trying to explain to you what's driving SLT, why we need it. It's at the moment, it's the examples I've given focus on the embedded software, as well as these complex boards we have to develop, mainly on single chips. So what does it mean for, I won't go through that. What does it mean for chiplets? And I'll come on to that now. Because one of the things we're working on with SLT is to push more of the structural tests. So before we talked about ATE, and we do structural tests like scan test inside an ATE, and it's very expensive equipment. A lot of the companies were developing SLT, and when they go to SLT for volume, want to do move some of their structural tests into SLT, because they see SLT as something they need to have in order to get their coverage up, their fault coverage up. So it's something they need to do. And they're thinking, well, why don't I make it more cost effective by moving more of the structural test into the SLT environment? Because ATE, the structural test they do on ATE is very, very expensive because the cost of that ATE equipment, and they measure test runs by the second. If they can shave off half a second off the amount of time they spend on the ATE, that saves them a lot of money. So they're always trying to do their fault coverage on less and less tests on their ATE because the ATE equipment is so expensive. So moving some of the ATE into the SLT becomes interesting. Only problem is that you've got to try and get the vectors on and off as fast as possible. And normally you would do that via JTAG, but there is a new standard come out called 1149.10 that allows us to speed it up. Yeah, go ahead. Question?
Yeah, I would have a question. So when you're describing to move tests from ATE to SLT, you're like, I'm assuming that you mean like the die would then be packaged in between and then tested in an SLT environment. Yes. So would, in your experience, does basically, like, if you package the part and then you find out it's broken, I would assume that increases the scrap cost. But are you saying that you would still have a financial benefit even with like higher scrap costs because now you're burning a package as well if you find a fault?
Yeah, so I guess it would do, the analysis all depends on yield, doesn't it, and how much of the what types of tests you move from that original ATE into the final SLT, so that and then what the yields you're getting from that final SLT is. So I don't think they'd move all of the testing in there because then you'd be binning high numbers of chips with that have been packaged, and you'd be losing that package cost. So yeah, I'm not sure they're going to move everything in there, but there's a potential cost saving as long as you're not having to bin too many packaged chips.
Gotcha. Okay, thanks.
Yeah. So you're right. It's a very good question, and I don't think there's a quick answer. It's all about analysis of yields and test times, etc. So it's but you could potentially see that if you can get 99% of 99.5% yield from your ATE, but you move half the tests into the SLT, and then you finish it all off in the SLT, your cost equation might come out positive by moving those tests. But it's
okay, so I think it's like basically targeting those tests that maybe have a lot of test time, but really only catch like the very occasional outlier, and maybe like addressing those in SLT.
Exactly, I think you summarised it. And these are engineers. As engineers, we have to do this type of thing all the time. But yeah, I think you captured it well in that sentence.
Okay.
Yeah.
Thanks.
And
hey,
so,
Mike.
Yeah.
So sorry, one more question. You know where you have the blue arrow,
yes,
from the HSTP test DMA into the cache?
Yeah.
What is that interface? Do you make that custom for each SoC that you're testing?
No, so this is So this is now sort of getting more and more. This is getting more where the SLTs.
Not the one you're circling, but
Let me explain this interface and I'll explain the blue interface.
Okay.
So what's coming across here is those structural tests. So those tests that you've moved from ATE into SLT, if you push them across the JTAG interface, it's a very slow interface.
Mm-hmm.
So what we're trying to do is push this 1149 allows us to stick it behind the high-speed SerDes, and so the chip we're working on at the moment, this is behind the USB interface, and so you've normally got the USB going here, but in test mode you can push them into this IP here. And then what this
is on die. You're burying this IP on die.
Yes, the IP is on die. Yeah.
Okay. It's IP on die. Never mind. Okay. Thank you.
That's it. Exactly. That IP has to go on die.
On die. Okay.
And sit. So you dual purpose your USB interface. Your USB interface. And some companies have an issue with that because USB interfaces are hard enough to design anyway. and then either having it for functional mode and test mode. Some people think that might be an issue, but we don't think we don't see it as a major issue. And then what all this is doing is pushing those structural tests that you would have normally done. You know, I could have drawn that line going up to sorry, that line going up to CPU and IP1 and IP2 is just happened to
Right.
Maybe I should make it more clear by drawing that blue line going to
No, it's the red IP being on die that I missed. Once it's on die, you can go anywhere. That makes sense.
Yeah. And so and all you're doing is pushing those structural tests into the various IP, and then take. But what this so I think that and if we were just talking, and then you can scale it like this. You've got the test handlers with the thermal control. You've got your master computer, and there's our single die, and that people often get confused. That I should maybe make this picture more clear that IP is on silicon, is on die, and there's the test handler there. And as I say, these test handlers can now go up to 500, 1,000 chips, so you can really scale SLT now. It's becoming very scalable, and therefore, if you're going to do it at that scale, then you can start to think about, can I push some of the EAT into this? But from a chiplet perspective, and I guess from our perspective, what's the potential interest here for chiplets? One, and this is maybe a good point for discussion, is that we could potentially, if we do put 1149.10 onto the IP, then we could do high-speed structural test in the chiplets as well, because I would have. So, for example, I don't know about whether it's suitable for a bunch of wires, but certainly for UCIe, if that's sat behind a high-speed SerDes, we could potentially use that in the final package chip. So chips could be talking to each other along a high-speed interface, and then we could do a lot more structural testing. So one of the chiplets could be a master chiplet that's feeding structural tests to those IPs that are in situ. And the other thing, which I think is just a normal SLT, is that once you've got a system of chiplets, then you can start testing that system of chiplets just with SLT. So you can start to put do system level use cases for testing those packaged chiplets, and then and then this allows you to do that. Yeah. Oh, is that the right one? Okay. So that would allow us to do that. So yeah. So that's all I wanted to say, Beppy. I think what I've tried to describe as what SLT is, because that may be new to some people, but also put it in if we put it in the context of where it might be useful for chiplets. I think one is that when we start to make systems of chiplets, SLT will be a very good way of testing those packaged chiplets systems. And there is a potential, if we're connected, if those chiplets have a high-speed connection and they're connected to each other on high-speed interfaces, then we could actually start to move some of the structural testing into those packaged chiplets as well.
So how does the USB, let's say that SerDes, that USB port, right? Does that then connect to a PC, or I was trying to understand the higher level. I mean, this makes a lot of sense. So
yeah, so we could do. I mean, that those they could be connected, or so that there could be a single USB interface coming into per chip.
Yeah, PCI Express or Ethernet, whatever, right? So it's some sort of a standard interface there, right? So, right. Okay, got it.
But also, I also think if we're connecting, if we're doing die-to-die connections across a high-speed interface, then one chiplet could be could be feeding structural test to another.
No, I get that, but you need one chip to
Yes.
interface to the outside world, and then you have your IP inside, and then IP then could go to, you know, UCIe or a bunch of wires or whatever, and then act as a interface to other chiplets as well. No, I get that.
Yeah.
This is quite compelling, actually. It's a great idea.
Yeah. And one of the projects we're working on has a sort of, if you look at it, you'd call it a master. There's a master chiplet and 16 slave chiplets effectively. So that master chiplet could be then saying, well, I'll farm out all of these structural tests to all of these slave chiplets, collect the results, and then feed them off back into the test environment, into the tester. And one other important thing which I should mention here, but that doesn't really come out very well on the slide, is the repair as well, because what you don't want to do is have 17 chiplets and one of them fails and you throw it away. What you want to be able to do is to see if you can repair that chiplet in some way. So you might also be wanting to then speak to somehow do a repair on that chiplet. So, for example, you may have redundant memories, and then when one memory fails, you quickly switch to the to the redundant memory instead, or you downgrade that chiplet as a lower performing chiplet. So because that goes back to the question about if we package things and then put them into a chiplet package, then aren't we wasting money if it fails? Well, if it's repairable, you can recover a lot of those costs as well. So, there's that aspect of it as well. Another aspect that might be important, I haven't really investigated this too much, is certainly in, for example, an automotive environment where you need to be continuously testing and trying to find faults. This could also be useful for that, this type of interface, because you could be feeding structural tests quickly to your chiplets and getting results. Certainly, the automotive chips I've worked on, you might want to be looking for intermittent faults, 10, 20 times a second, and getting high coverage to try and see if there's any intermittent faults. So this could play into that, though we haven't investigated that at the moment. This is still more about testing chips as they come off the production line, rather than testing them when they're in the field.
Yeah, but I do think your idea here is a lot of merit. I may reach out to you because I have an application where we're talking to a customer, so I'll probably reach out to you, Mike.
Yeah, sure. Who is that? Sorry, I can't see who's speaking.
Cash Johal with Etopus.
Okay.
I'll ping you.
Yeah. So I think SLT is relatively new. Let's say relatively, but I think it's been mainstream. A lot of companies been investigating 3 or 4 years, 5 years. So it's still people trying to work out how best to use it, and how to get it high volume. But it is going to be important to try to allow us to get the fault coverage that we need. And as I say, there's this play here where you can put high speed test interfaces on, or you're just trying to, you're just running a lot of embedded software to try and find the bugs that you can't find in structural test. Or the one I spoke about at the beginning is the customer just saying, well, I don't know, I know my structural test has got holes, but I don't know what they are. If I go to system level test, I can find those holes and then design a structural test for that system level test and push that structural test back into my ATE. So I don't need to go to high volume SLT, but I can use SLT as a test development flow effectively. So, okay, Bappy, I don't. Hopefully that was useful.
That was actually useful. You got Kash happy, so he's a pretty high bar from what I can see. So,
Okay. Yeah.
right, Kash?
I would have one other question, Mike. Could you explain a little bit more what this SSN is?
Yeah. So that is that's a streaming. I can't remember exactly what it stands for. It's gone slipped from my mind. But basically, when you do these structural tests, you need to stream them. So it's a streaming structural network or something. It's a format that allows you to get those structural tests, which should normally just be a scan chain. But you obviously, what you need to do is put them into a sort of USB packetized format, and it comes across, and that's what SSN is. I think it's a format from Siemens. I always think of Mentor, but of course it's Siemens now. But it allows you to packetize those structural tests, if you like. So normally those tests would just be run across the JTAG as a scan chain. But as soon as you start pushing them across a USB interface, obviously the format has to change.
Okay, thanks.
And that's what SSN is there for that format change. Okay. I only ever hear it within the context of Siemens. I don't know if it's a Siemens only format or if it's an industry format. Yeah.
I think Synopsys has their own.
Yeah,
Yeah,
Synopsys has an equivalent streaming fabric to that.
Yeah. So it probably is Siemens only. So, I think it's it just depends what tooling you'll use as to what format you'll get out from it.
Okay, makes sense. Thanks.
Okay, thank you. That's all I have, Bappy. So hopefully that was useful.
Yes, it was.
Okay.
Thank you.
Okay, thank you. I'll stop sharing at that point and hand it back to Bappy.
Any other questions for Mike? Okay. Well, in that case, thank you all. Have a good rest of the day and a weekend.
Thank you. Oh yeah, thanks for the opportunity as well.
Okay.
Thanks, Bappy.
Thanks, Mike. Appreciate it.
Thanks.
Thank you.
Bye.
Thank you.
Hey, Kash, if you need Mike's email address, I can connect you. Or Mike, if you're still on.